Welcome back, class, and this recording is going to focus on solving some problems and examples related to sections 5.4 and 5.5 in the MOSFETs chapter. So we are still on week 10 material, yep, and the last lecture we covered 5.4, section 5.4 from the textbook, MOSFET amplifier design, and also section 5.5, small signal models. So the examples and problems I'm going to look at today are about this material. Okay, so let's get started. One thing I wanted to point out before we jump into our first problem. So I'm on slide 43 and you can see all the items for 5.4, and one of the important items is moving ahead to slide 45, where we have our main VTC graph that shows how the relationship between VGS and VDS plays out. So VGS is the gate to source and VDS is the drain to source voltage, and as you can see, as VGS increases, VGS is the on the x-axis, the independent variable, VDS falls, and it falls through the three regions: the cutoff region, the saturation region, and the triode region, right? So I've tried to put everything here together so that we clearly understand these three regions. But the one difference, one point I changed was with regards to point B. I had written that at point B we have VDS greater than V over voltage, VOV. Um, Also I had written over voltage or over drive voltage as OD. It's actually VOV. That's the right way to do it. Anyway, the change I made is to, instead of writing VDS greater than VOV, I changed it in this way. VGS equals VDS plus VT at point B, because that's the way in the textbook he describes it. He says at the point V, at the point B, which is the lower limit of the this curve, the saturation region, at B, VDS becomes lower than VGS by VT. So that's the right technical way of saying it. And if you translate this, it just means that at that point B, if you take the value of VGS and compare it to VDS, you'll find that VGS is VDS plus VT. So the x coordinate and the y coordinate at point B are related to each other in that way. So it's a slight difference, subtle difference, but that's the way it's in the textbook, and I thought it's important to make that correction. Okay, so with that clarification, I'm actually moving on to slide 49, where we have our first example of this material. And this example is example 5.9. I think it's an important example, so please pay attention and make sure you understand all the subtle details. So he says, consider the amplifier circuit shown in figure 5.29a, which really just means, let me open that, this circuit, right? This circuit with both the biasing voltage and the signal voltage shown on the input side, and similarly on the output side you will have to calculate VDS, which is the sum of the biasing drain to source voltage plus also the output signal, right? So and then the graph is very helpful, because we will be looking at points Q, points B, the swing from Q to B on the input side, on the output side. So all that is part of this question. So anyway, let me go back to my PowerPoint and then I'll come back here. Yeah. So that is the circuit. The transistor is specified to have all these values. Vt is given, K is given, W by L. Luckily lambda is 0, so that means we don't have to worry about that correction because of channel length modulation. Also VDD is given, the biasing battery. The resistor in the drain circuit is given, VGS is given. So lots of things are given, so that kind of makes it easier. Part A says for VGS, that means the signal on the input side is 0, hence the signal on the output side is 0. So all he wants us to find is the overdrive voltage ID, VDS and AV. So what I'm assuming, he doesn't specify exactly that this is the Q point, but the way the problem is written, I'm summarizing that, yeah, I have this diagram also in my notes. So what he's wanting us to do is to find Q, the coordinates of Q. He's already given us one coordinate. He's given us VGS and he wants us to find VDS. So first point is to find the biasing point Q, and then he wants us in part B, he says what swing is allowed. That means what is the maximum input swing of this signal voltage so that we are still in saturation. That means we are still linear. Okay, so that's the problem. Okay, so let me go back to the problem. Yeah, so so we have all this. Part A again just says zero signal, that means just focus on the DC bias and find all these values. I've listed all the formulas that you're going to have to use, or he has used in the textbook, to solve this problem. I know this is an example, I shouldn't be spending too much time because you can read it, but again this is important. There are some important ideas and concepts, so I wanted to take some time, okay, and walk through the details. So first of all, we need to find this over voltage, right? The overdrive voltage. Simplest formula is this. Secondly, we need ID, so that's the formula. Then we need VDS, so that's the formula, and AV, that's the formula. So we have 4 formulas and 4 calculations to be done. And so let me show you that he's done exactly that. First step, GS is given, VT is given as 0.4, so over voltage is GS minus VGS minus VT, you get 0.2. Next step, find ID, use this formula, you get 0.08. Third, use this KVL rule and find VDS. Fourth, use all these parameters Kn, VOV and RD to find voltage gain. Okay, so part A is pretty simple. It's just mechanical. Substitute the values and you get your results. Part B is where we get a little tricky. Sorry. Yeah. Part B, what is the maximum symmetrical signal swing allowed at the drain? Hence, find the maximum allowable amplitude of a sinusoidal VGS. So what this means basically is, first of all, he says, given that we know Q and we can guess at B, he hasn't told us to find B specifically, but kind of implied that you can figure out B. So if you know Q and B, now remember there is the output side and the input side, right? So on the output side we are talking about the drain to source voltage, VDS. So how much swing is allowed, right? Q to here, and similarly on the positive side also. Both sides going up in value for VDS and going down in value for VDS. What swing is allowed without going into this portion or this portion of the graph, without becoming nonlinear, basically. That is the question. And once you know how much you can swing this way, you also can find out this swing, right? Because this swing and this swing are related by the amplification factor. And this swing, of course, is this. So instead of having a triangular waveform, he says use a sinusoidal. It really makes no difference which one, okay? So that's the harder part, part B, okay? And I've just shown you the summary results, right? If this is the input signal, this should be the output, right? And of course there's a phase difference. When this is going high, this should be going low, right? So let's see what he does to solve part B. Let me do this. Yeah. So first of all, how do you find, now first part of the question says find the output swing, then find the input swing. The output swing is the DS swing, right, drain to source voltage. So he says, since we know that at the Q point VDS is 0.4, which we just calculated here, right, where is VDS? Yeah, VDS we calculated as 0.4, which is the bias point, which is Q. So VDS is 0.4, and how do you guess what the B point is, right? The lower cutoff or the saturation limit, B as in boy. So for that he says just use VOV equals 0.2 volts, because he has given us V over voltage or over drive voltage 0.2, and so you can swing from 0.4 to 0.2, right? That means you are allowed a negative swing of 0.4 minus 0.2, which is 0.2. Similarly, if you think it's a sine wave is symmetrical, right, on both sides. So if you're going 0.2 on the negative, the positive also you go 0.2. And so on the positive side, you add 0.4 to 0.2, you reach a limit of 0.6, right? Now that is not a problem, because only until you reach VDD, which is what is VDD, 1.8, is when you go into cutoff on the upper side. So that you don't have to worry about upper side. Generally in these problems you don't have to worry about the upper swing on the output. It's only the lower that causes problems. So because of the way the curve is. So anyway, on the lower side we are allowed minus 0.2, and on the upper side plus 0.2. Okay, so that's how he derives it. Now one thing that I found a little surprising is why he hasn't found out B, this point B, using the formula, right? We have a formula to find B. Let me take you there. Yeah, see, we know we can find the I'm on slide 45, by the way. We know we can find B, both the coordinates, we GS at B and we DS at B, by using this formula, and all these values are given. So I wondered why he didn't take that approach, but he hasn't. I calculated it myself just to check, and I got a slightly different value. So in the example he came up with a value of 0.2, right? I came up with 0.817, so I'm slightly off, because he takes the DS voltage limit on the bottom as 0.2, but if you calculate the same point B, and you find the coordinate VDS at point B, you get 0.213 instead of 0.2, right? So on the lower side, 0.213, so 0.4 minus 0.213 gives me a smaller swing. So anyway, you can do it either way. I think you'll get slightly different results, but both I guess are valid, because we are still doing approximations here. But this is the way he does it, and I hope you see the logic he used. Okay? Alright, so now that we know the swing on the drain side, on the output side, what is the swing on the input side, the signal? So to do that, all you have to do is take the swing on the output side, divide by the voltage gain, and luckily we already have the formula and we have all these values to find the voltage gain. So just divide by that, so you see the swing on the input side. So basically for a 14.2 millivolt swing, you get a 200 millivolt swing on the output side, which is because of the gain, 14 times gain, right? So that solves the problem. You can easily put the values here and you can see, what is the input and the output, and they have to be obviously out of phase by 180 degrees. So one other thing he does, which I find also a little interesting, he has used another formula to connect the drain saturation um, coordinate and the gain, uh, I mean drain saturation and gate saturation voltages. They are still linked by this Vt factor, right? But he has used a slightly different approach, and I don't know where this formula came. It must be in the textbook somewhere. I didn't think it was important, but using this and some more calculations, he's able to prove that instead of this 14.2 on the input, it's actually 13.3. So there's a slight error. And he says this is a more precise result than that. So, plenty of things to learn in this example. I hope you can pay some attention and make sure you understand the main concepts. Again, part A is just mechanical. You can just plug in the values and get it. Part B, how he calculates the swing on the output by taking this value at the Q point, subtracting this value at the B point, which he doesn't call it B, but he just uses the over voltage as the representative of the VDS at the B point, takes that difference and he uses that as a swing. Okay, all right, so I'm going to have to move on, but that was an interesting problem, I thought. I have another problem which is quite similar, also from the textbook, but from the back. You'll find a lot of things are similar, but there's slight differences also. So what is this problem? He has given us the same circuit, and again VDD value is given, RD is given, this K process parameter is given, VT is given. So lots of things are given. Sorry. Oops. Yeah. And I'm on slide 50, by the way. So the way he asks the question is slightly different though. Here he tells us, part A, find A and B on the VTC, right? So he is advising us, even before we begin finding the Q point and all that, just find A and B. So that makes it a little bit easier because you know the limits of the swing now. And in part B, he gives us a little more detail and he says, if the amplifier is biased to operate with an overdrive voltage of 0.5 volts. So instead of giving us, the biasing coordinates, that means the input VGS and the output VDS, or even the biasing current ID, he gives us the fact that the overdrive voltage is 0.5. So when the amplifier is biased at a certain point, at that point the overdrive voltage is 0.5. So he gives that fact, then he asks us to find the bias point. And of course the current, the bias current, the gain AV. So all this looks like the previous example. Only thing is we first are asked to find A and B on the VTC. Okay, and then he again says, okay, what sine wave can we put on the input side on the VGS so that the transistor remains in saturation and doesn't become nonlinear. Okay, and he says actually to calculate the gain two ways. using this formula and then using the actual output by input, and then see if there's a difference and explain why. So it's an interesting problem. So I have my PDF where I have this solution, and so let's look at that together to understand how to do this. So here's the drawing of the circuit and of course the simple graph. So he has given all these values. Part A, we have to find A and B, right? So A is pretty easy, it's just the cutoff value, and here VGS is just VT, ID equals 0, and if ID equals 0, the VDS is just VDD, the source voltage, which is 5 volts. So the coordinates of A are 1 and 5. Okay, 1 is the VT or VGS actually, and 5 is the drain to source voltage, which equals VDD. So I don't think we have calculated it before, but calculating A should be easy. I hope you can see how we do that. Point B, we use the formula. So I used this formula and came up with VGS B first, which is 1.605, and then to find VDS, so this is the x coordinate of B, this is the y coordinate of B, you just subtract the VT. So B's coordinates are 1.605, which is x axis, x coordinate, and 0.605 the y coordinate. Okay, so that's how I calculated B. Now we come to the more interesting part, which is, now that we've been told that at the bias point the overdrive voltage is 0.5, right? Find Q, the coordinates of Q, and then find ID and AV. So since VOV at any point is the VGS minus the VT, VGS comes out to be 1.5 because VT is always a constant, right? It's given as 1 volt in this case. So VGS we know. Once you know the overdrive voltage and the other factors, you can find the current also, the drain current. So that is found. And then to find VDS, you use the basic formula, this formula, the KVL on the drain side. So you come up with 2 volts. So Q point, it has 2 coordinates, 1.5 and 2. Both are voltage. AV is just the simple multiplication of 3 things, and that comes out to be minus 12. So that was part B. Part C is where we need to find the amplitude of the sine wave on the input side, and correspondingly what happens on the output side. And we obviously want to stay in the linear region. That means we want to be in saturation for a NMOS transistor. So how do we do this? So we know we can swing from Q to B, and we luckily have both these coordinates already calculated. For Q it's 1.52, for B it's this, right? So that is, we can swing between these two. So if you're calculating the swing on the input side, you have to look here, right? What change in VGS happens? So VGS can go from Q to B, maximum on this side, positive side, and it can go symmetrically same amount on this side, right? And this is far away compared to how the distance QB, QA is much farther. So this side we never have any problem. This side is where we have to watch out for. So the swing on this side is like that, right? And then on the swing on this side is like this, right? Or rather, it goes like this to like that, right? Okay. So that is, sorry, yeah, I tried to draw that and I made a mistake. I put both of them in the same direction, so you have to excuse me. Obviously when this goes high, this must go low, but I hope you get the general idea that there is amplification and the output is much bigger than the input. But the phase I made a mistake, so please forgive me. Okay, so how do you find the swing? So the VGS can swing from 1.5 to 1.605, right? You take these coordinates, the first x coordinates. So 1.5 to 1.605, the maximum amplitude is, you take the difference of these, it's 0.105. On the other side, it can swing symmetrically. So 1.5 to this value, 1.395, and see how I calculated the lower limit, right? So bottom line, the swing is from 1.395 to 1.605, with 1.5 being exactly in the middle, which is the Q point. And this is on the input side. On the output side, you could have used the amplification formula, right? But we've been asked to do it both ways. So what I did is, for this VGS, I found the ID and I found the exact VDS. And the other point, the Q point, no, the B point, right, which is the lower limit, we already know what the VDS is. So there I didn't calculate. So just calculating for uh, uh, the lower point of the VGS gives me the high point of the VDS as 3.175, this point, the top point. And then I look to see what is the delta in the output and by the delta in the input, and I got minus 11.7. So if you compare this calculation to what we got here as the voltage gain, which is minus 12, so instead of minus 12, we got more precise minus 11.7, which is about 2%. And the reason they are off is because of the nonlinearity factor. Okay. So I hope you can see how I did this, and if you have any questions, do let me know. I'm going to pause for a minute. Okay, so I think we're done with that example, and let's move ahead to the next section, where we look at some small signal models and some problems related to that. So I'm skipping past some slides, 52, 53, 54. Yeah, on slide 54, I wanted to point out some formulas for gain, and we'll use some of these in the next examples. In fact, here's one unique formula for AV. Now, AV is just output voltage by input voltage, right? It can also be written in this form, because IDRD is actually also representative of the output signal, right? The voltage drain to source is linked to, using KVL, is linked to the biasing voltage or supply voltage VDD through this element. So this is another important formula. uh, Here are a bunch of formulas for how to calculate GM, transconductance. So we'll be using some of these. GM in terms of the overvoltage and Kn, GM strictly in terms of these process parameters and the aspect ratio, the drain current, GM in this fashion, GM also calculated as this way. So a variety of formulas, you just have to look at what data is given and find the appropriate formula to use. Okay. Okay, so I'm on slide 58, where we have a very simple formula of problem. I found it not in our textbook but somewhere else. But let's see, let's start with this. So what is the question? A MOSFET is biased at a drain current of 0.5 milliamps. So that's all is given. You have the drain current, meaning ID of 0.5 milliamps. The rest of the information has to do with the parameters, the process parameters, aspect ratio, and also a lambda is given. So we have to find RO. Remember, RO is used to adjust the model, the small signal model, to take care of the channel length modulation effect. Okay, so all we are being asked is to really find the small signal parameters GM and RO, right? If you go back and look at slide 56, where we have this small signal model, we basically need to find GM and we need to find RO. Okay, so it's a straight plugging in the values that have been given to come up with GM. In this case, GM, I'm using this formula and I come up with 1 milliamps per volt. On this side, I'm trying to find RO. RO is related to lambda and the current, the drain current in this way, and so that comes out to be 20 kilo ohms. So this is a very simple problem, not much need to spend time here, but this introduces you to some more complicated stuff later on. So let's move on to slide 59, where we have a good problem, more complex, and this is from the back of the chapter. So let's read what it says. So an NMOS amplifier is to be designed to provide a 0.2 volts peak output signal across a 20 kilo ohm load, which is also the drain resistor. Okay, so we have a classic circuit, NMOS circuit, with a drain, and I didn't copy it here, but you can visualize the circuit, right? So there's a VDD that supplies the bias, and the drain resistor value is given, which is also the load resistor, and an output signal has to be 0.2 volts peak or 0.4 peak to peak, I guess. The gain has to be at least 10. That means on the input side, the swing on the gain to source signal is 1/10 of this 0.2, right? That's what it means. So given all this, what is the GM is one thing that's being asked. Secondly, using a supply voltage of 1.8, so the VDD is given as 1.8, what values of ID and VOV would you choose? Then he says, to achieve all this, right now, ID depends on all these factors, the aspect ratio, the process parameter, and the over voltage. So the one thing we don't know is W by L, the ratio, so he says find that. Lastly, he says, for a given biasing, find what that GS will be, the big GS, okay, the DC GS biasing signal. So all this has to be found. So let's go to my PDF and we can quickly look at the solution. So this is the example and this is the problem. So given RL is 20K, the circuit, I haven't drawn it, but obviously it's going to look like this, right? You have an RD, you have a VDD, you have a VGS, we have a VGS. The output is the drain signal, drain source, VDS, that we have to find, and there's an ID, and we have this nice formula that we use all the time. So it's pretty much the same circuit. I didn't draw it again, but here we are. Okay. So we are given that the drain to source or the output voltage signal must swing plus 0.2 and minus 0.2. First step, find GM, straightforward formula. We have gain is given as 10. So given that, use the simplest formula and you come up with a GM of 0.5 into 10 to the power minus 3 amps per volt. Okay. Next step is find V over voltage, because we are hoping that once we have over voltage, then we can work backwards to find ID and find a biasing points, right? So to find over voltage is a little tricky, because we can't use any of the formulas directly, right? So VOV appears in this formula, for example, but we don't know VDS. We don't know ID. So many things are unknown. So you have to look at the available data, and you probably need to set up at least two equations in two unknowns and then solve, right? So that's exactly what is going on here. So the first equation, I've used this formula, and to find VOV, you know, I transfer VOV here and take gain towards the bottom. So this is then 1.8 minus VDS by 5. So I have unknown VDS, I have unknown VOV. So how do I find another equation? So one other equation is, we know that the output signal has a peak of 0.2. So the VDS that we are interested in, right, which is the total VDS, which is the sum of the DC plus the AC signal, also has a VDS in it, right, the big VDS that we need here. So the big VDS then becomes VDS equals VDS minus this VDS. Now we know that at saturation, which is the lower limit, we can replace this total VDS, right, to be V saturation or V over voltage, because at saturation, which is the lower limit, which is the point B in our graph, right, we know that the VDS has to be this over voltage, over drive voltage, right? So what we are doing then is, in this equation, we take this VDS to be the overdrive, and which is still an unknown, but we can at least substitute overdrive here, and the small VDS we know is minus 0.2. So if you take overdrive minus of minus 0.2, you have an expression for this VDS, which is the biasing VDS at the Q point, to be VDS equals V over voltage plus 0.2. Okay, so follow this logic. It's a simple, I think, easy enough to understand. So we have created two equations with VOV, right? One is this and one is this. So what I will do is, I will take this equation for VDS and plug it in here. Then we can write V over voltage is minus 1.8 minus this by 5, and you come up with V over voltage equals 0.27 volts. So just remember, the logic here is pretty straightforward. All it means is, at the point B, which corresponds to the lowest point for uh, both coordinates of point B, right? Both the input swing and the output swing, that means the VGS and the output VDS, both of those are at point B, and at that point we take the output voltage, the VDS, to equal the saturation voltage, right? We know, not the saturation, the overdrive voltage, right? We've always said that at the start of the saturation region, the drain to source voltage will equal the V over drive. So that is exactly what I've used here. VDS, the output voltage, will be the overdrive at the point where you're entering saturation. And if you use that condition, then you can write this original equation in this way, using the overdrive voltage and the signal value. And then you plug that back into this and you get the value for overdrive. Once you have overdrive, you can calculate ID using this formula, the drain current. I've tried to explain some of my thinking here, so hopefully that helps you. And then to find the ratio W by L, I use another straightforward formula. And then to find VGS, I use another formula. Okay, so W by L comes out to be 9.19 and VGS comes out to be 0.61. So hopefully this was helpful. This is another way to use to determine the signal swing. Luckily we are not asked to find anything on the input side here. We have only been asked to find the swing on the output, which is the drain to source swing, and we were already given a negative value of the swing, but we had to find the biasing condition, and to find the biasing condition we needed the overdrive voltage. Once we have the overdrive voltage, you can find he didn't actually ask us to find VDS specifically. You can plug this in, right? 0.27 plus 0.2 is 0.47. That would be the Q point value, right? And we haven't been asked to find that, but we were asked to find the ID, so there is your ID, and of course some of the other stuff. So it was an interesting problem. I hope you benefited. I'm going to pause one more time and come back in a second. So I hope this problem was interesting and you followed along the solution. If you do have any questions, feel free to reach out to me. Let's move on. So this was slide 59. I have one more problem on slide 60, an example actually, and this is in your textbook 5.10, and this is the last problem we are doing in this recording. Nothing more after this. This is a nice example with lots of interesting pieces of information and knowledge that we can gain from this. It's a little bit long, many things to do, and some very new ideas that are coming our way. But overall, I think you will find that if you go one step at a time, it's not very hard. Okay, so first thing I would like to point out is that the circuit diagram has these capacitors, right? I know we have seen these before when we did our BJT examples. These are coupling capacitors, and basically all we do is ignore them when we do our circuit analysis, because it's assumed that the coupling capacitors block DC when they have to, when we are doing small signal analysis, and they are only relevant. They kind of behave as short circuits when we are doing small signal analysis, is the point. So you might as well just totally get them out of your mind right away. Otherwise, there's some interesting pieces of, one more interesting aspect about it is how the gate bias is being derived. We haven't done too much in the way of biasing. Generally, we assume that there is a VDD source, right, on the drain side, and we have some kind of battery on the gate side, so that we get a VGS either through a resistor directly or just grounded, etc. But in this case, he's showing us a form of biasing using a resistor in the gate circuit, and this resistor actually is connected to the between the gate and the drain circuit, so it's kind of a voltage divider type arrangement. So there's not too much here to analyze. He says you'll study more about this biasing later on, So all I want to point out to you is that there are many biasing arrangements, and we've only dealt with a few so far. Hopefully you'll learn more about it in your next course. But in this case, that 10 mega ohm resistor, it's a large resistor, is right there, and it's kind of new to us. Okay, so with all that background, let's quickly read what he wants and see if we can proceed. I know we are running again up against the clock. But give me 5 minutes and we should be able to wrap this up. Okay, all right. So this is a discrete common source connection of a MOSFET amplifier, an NMOS. What is a common source amplifier? That also you'll learn later on, not in my course. The input signal is coupled to the gate via a large capacitor. We talked about the capacitors. And the output signal also has a capacitor connecting to the load resistance RL. So there's a load resistance also in addition to the big gate bias resistance, plus of course RD. We wish to analyze this amplifier circuit to determine its small signal voltage gain, its input resistance, and the largest allowable input signal. I guess we haven't really done too much in the past about input resistance, right? That Rn that you can see at the bottom. So that's something new also. Then the transistor data is given, Vt is given, the process parameter is given, and Va is given. Va meaning we have to take into account some channel length modulation effect. So he doesn't mention it, but here in the solution, the writer has used the small signal model to answer questions. That's why this is in this place in the chapter. It's just after, we have studied all these models. If you go back to slide 56, there's a model there. And then GM, there's a lot of formulas for how to calculate GM, the transconductance, and of course RO, we did a problem. So bottom line, we have to be able to create some small signal models. Okay, so I'm going to go to the text PDF and we'll see how he solves this problem. So you see that he's already given us 3 drawings after the main circuit drawing. So he's given us, so that main circuit was part A, drawing A, then we have B, then we have C, and then we have D. So you can see how the answer will be evolving, right? How we'll come to the final stop using B, C, and D. So A is the original amplifier, B is a circuit for determining only the DC point, the bias point. So the signals are kind of blocked by the, we pretend that they don't exist. And then we put the small signal model here. And lastly, we simplify the small signal model to answer some questions. Okay, so first of all, he says let's determine the DC operating point. So even though we only want the small signal values, right, like gain and so on, and also the allowable input signal, that kind of stuff, we cannot avoid obviously having to do the DC analysis and coming up with an operating point, a Q point. So the first part of this is just to do the DC analysis, and to do that he uses some familiar equations, right? Oh, one other point is that because of this connection, the gate to source voltage equals drain to source voltage, because no current flows into this, right, the gate circuit, and there are no other voltages in the gate. So where does it get bias from? Whatever is here is also applied here. So that's one convenient way of biasing. It has its problems, but in this case that's what we're using. So almost the first thing he says is we know that since Ig equals 0, the DC voltage drop across Rg will be 0, and hence VGS, the biasing at the gate, will be equal to VDS, the biasing at the drain or the output also, which is VDD minus RDID. So also another fact he points out is that VDS equals VGS. With VDS equals VGS, the transistor will be operating in saturation, right? So this is an interesting fact. Think about it a little bit. If you're confused, let me know, but this makes it convenient. So the transistor is in saturation, and so we can find ID just by using this formula, right? So for this calculation, he's neglecting the channel length modulation effect and just substituting all these values. You actually come up with a quadratic expression because it's an equation in the square of VGS. But he says one of the two solutions will be not relevant when you solve for ID. So just take the other one. So he takes that, and that's 1.06. Once you have this, you can plug that back into this and come up with into this formula and come up with VDS, which is also VGS, which is 4.4, and hence the overdrive voltage is one of these, VGS minus VT, which is 1.5 volts, and you get 2.9. So in this part, the top part, he has found various DC biasing values. The drain current, the VGS, the gate to source biasing voltage, the VDS, which is the drain to source, and the overdrive voltage. So all these are part A. Now let's see what we need to do for part B. First of all, we need GM and RO, right? So for GM, transconductance, he uses this formula. Everything is given, we just found VOV, so plug that in and you come up with GM, and then you come up with RO. Okay, so now, and that was using this drawing, we found all the DC stuff. Next, he draws the small signal model, right? Some of this we already know, right? Generally in the model we have this dependent current source, the voltage dependent current source, and we also know RO. Both these come together, so the shaded portion is something we are familiar with. The new stuff is this resistance RG, right? This resistance appears like this. Now because there is no other resistance, this almost seems like in series, right? Really it's a parallel resistor, but hey, there's no other resistance, or this resistance is always 0. So we have like one resistance on the input side. On the output side, we have two other resistances in parallel. There is the RD, which is drawn like this. There is the RL, which he told us there is an RL, right? This RL. So that RL, so all this is in parallel. So this makes it a pretty simple circuit. And now we can start, simplifying this using standard series parallel methods and so on. So that's what he does. In part D, he takes these three, clubs them together to come up with RL prime as one resistance, and then we have RG, and that's it. It's a simple circuit now to analyze, right? R input, right? Now that's a new thing that we have to find, and that he defines it as, which is the input impedance is VI by II. That means the voltage looking from here divided by the current into the circuit from the source. Remember, this is only the small signal. We are ignoring the biasing stuff at this point. That gives you your small signal input impedance. Okay. So to solve all that, he goes through a few steps. So this we talked about. He actually does a derivation to come up with a simplified value for the voltage gain. Okay. Finally, it turns out after all this manipulation that the voltage gain is a simple minus GM RL prime, right? Normally we can use AV equals minus GM RO. I think that is the equation, right? Yeah, somewhere here. yeah, AV equals minus GM RD, or RD in parallel with RO, right? That is the voltage gain. And so here what he does is the same approach, but instead of just RO and RD in parallel, now we have all three in parallel, and the formula still applies. So with that approximation, we get AV equals minus 3.3. So we have the gain also now. Now, to find the input impedance, he manipulates some stuff, and he comes up with this nice formula, and plugging it in, we still get 2.33 megohms as the input resistance. Then we have to find the largest signal that is allowed on the input side without driving into nonlinearity. So to do that, he uses the same method we always used, which is, uh, uh, on the input side you should be in saturation, which means VDS minus uh, uh, V the gain times the input swing gives you the output swing, right? So if you take the DC bias drain voltage and subtract the output signal, that should equal this overdrive value, right? The VGS minus VT. So using this equation and substituting certain values, he comes up with the maximum swing on the input side to be 0.35 volts. Okay, so lots of little pieces of interesting information, calculations. Please look through it, make sure you understand. I mean, this is too complicated to give you in an exam, so you don't have to worry that such whole thing will appear. But definitely there are little pieces in here that are important and that you might need to learn so that you can feel that you know that it's a subject. I do have a problem also related to a small signal model that I'll give in your homework. So with this example and the homework and the other problems I've solved, you should be reasonably well acquainted, and that you well understand this whole business of small signal models for MOSFET devices. Okay, I think with that we are done with what we wanted to do for this chapter, and next week, week 11, we'll move on to the next chapter in the textbook. Okay, bye.